Welcome everyone to another interview of series of interviews conducted by the Department of Chemistry, University of Colombo. I'm Pooja Kodituwakko. Today, Hashini Franciscus and Chani Sahabandu also join as interviewers. We all are undergraduates who are reading for a special degree in chemistry at the University of Colombo. Today, we will be interviewing Dr. Stuart Cantrill.
Dr. Stuart is the chief editor of the Nature Chemistry. He's a graduate at Birmingham University in UK. He obtained his PhD in chemistry from University of California, Los Angeles in 2001, followed by postdoctoral research at Caltech. His main research interests are in the fields of supramolecular chemistry, self-assembly processes, and interlocked molecules.
Hello, Stuart. We warmly welcome you to our interview. And thank you so much for giving us your precious time out of your busy schedule. These days, we all know that the world is suffering from COVID-19. Hope you are staying safe and doing great. First of all, I would like to know about your background of becoming a scientist. For example, I want to know about your educational background, whether your other family members have an interest in science or not.
So, well, first of all, thank you very much for having me here today. It's a pleasure to chat to you. So, no, neither my mum or my dad were scientists, and it was just something that as I was growing up, I was interested in how the world worked. And my mum was very keen for me to be a medical doctor, but I'm terrified by the sight of blood, so that was never going to happen. So it seemed like science was a good idea in terms of trying to get a handle on how the world works. And I really enjoyed science subjects at school, like physics and chemistry and biology. But again, because of the whole not really wanting to go into medicine, it was really a choice between physics and chemistry. And actually, when I first went to university, I first went to study physics. But unfortunately, and I apologize to any physicists who are listening or watching, I found physics very boring, and I left after a week. And I took a year off to think about what I really wanted to do with my life. And I decided, well, if physics didn't work, I'd try chemistry next. And so chemistry just kind of stuck. And so I loved it from the moment I started studying chemistry and started researching chemistry. And my life still very much revolves around chemistry.
Glad to hear about your science background, Stuart. Let's move on to our next question. You obtained your PhD in chemistry from UCLA in 2001, working with Fraser Stoddard, who shared the Nobel Prize together with two other scientists in 2016 for the design and synthesis of molecular machines. How did this experience mold your career path?
Yeah, so I was very lucky graduate at the University of Birmingham in Fraser's lab. And as an undergraduate chemist, I had no idea of his reputation or the kind of research he did or how well respected his research was. I was just happy to be doing research. And then when the opportunity came to do a PhD, because I'd already done some work in his lab, I just went into his office one day and said, I'd quite like to do a PhD with you. And he was like, yeah, sure, you can do that. He did actually say, you should go and look at some other, it was a great experience. I was in a large group with lots of people from all over the world, and we were all studying various different aspects of supramolecular chemistry and self-assembly. I actually never worked on molecular machines. So the thing that Fraser actually won the Nobel Prize for in the end, I didn't actually work on that. But it was just a very stimulating group to be in. The fact that Fraser went on to win the Nobel Prize, it's fantastic. I think it's great. I mean, it didn't really have, it didn't change what I learned in his group. He was a very good mentor, and he taught me a lot about chemistry and a lot about writing as well. And so, but the thing I really enjoyed working in his group was actually, while I did enjoy the research, I also enjoyed the reading and the writing side of science as well, putting the papers together, putting the grant proposals together. And it was that experience, I think, that ultimately led me on the path of becoming an editor. So that's kind of how it shaped where I ended up.
Very interesting, Stuart. My question is, your main research interests were in the fields of supramolecular chemistry, self-assembly processes, and interlocked molecules. What led you to pursue these fields?
So this can be traced back, excuse me, to this can be traced back to my very first lecture as an undergraduate student at the University of Birmingham doing chemistry. And it was Fraser who gave the very first lecture I ever sat in. So just as a first year undergraduate. And he was meant to be teaching us, I guess, introductory organic chemistry and things about stereochemistry. But he didn't. He likes to break the rules, Fraser does. And he was head of department at the time, so I guess he could break the rules. So instead of giving us an introductory lecture about what we were going to be learning about, he spent the entire first lecture telling us about his research, I guess to try and get us all excited by what you can actually do in chemistry. And so he spent the first lecture telling us about these molecules you could make that had interlocking rings or things threaded through other things. And he showed an example of this molecule called olympiadane, which, if you know the structure of the Olympic rings, 5 interlocked rings, they just made that in molecular form in his laboratory. And it had never even crossed my mind that you could do this sort of thing. In fact, it blew my mind that you could start threading molecules one through another. And I just sat there thinking, wow, this is quite cool. And I guess it was from that point on that was the aspect of chemistry I was really fascinated in. And not just, so supramolecular chemistry and self-assembly are things you need to know about to be able to make interlocked molecules. To be able to thread one molecule through another, you need to design molecules that can recognize each other so they can thread through each other and so they can self-assemble. So that's where the self-assembly and supramolecular chemistry comes in. But it was just crazy. You can thread one molecule through another. Who thought that was possible? And then talking about the different sort of things you can do with these systems, you can turn them into machines, you can maybe do molecular computation with them. That's where it all stemmed from. It was literally my first ever chemistry lecture was what set me off on that particular path of chemistry.
Those fields are really interesting, Stuart. Research accomplishments and publications. I have seen many articles related to supramolecular chemistry, and I saw some articles about supramolecular daisy chains. Can you give a brief idea about the supramolecular daisy chains?
Sure. So it's very much an old-fashioned idea, daisy chains. It's something that I guess children used to do before they had iPads and computers. So what children would do many years ago is they would pick daisies, the flowers, and you pick one daisy, and what you would do is you take the stalk and you'd split the end of the stalk to make sort of a ring in the stalk, a little hole, and you get a second daisy and you'd thread the stalk of the second daisy through the first stalk with the hole in it. So you start forming a chain, and then in that daisy you've just threaded through, you'd split that stem and thread another daisy through, and then you'd split that stem and thread another daisy through, and you could make these things called daisy chains. And the idea is we would try and make this with molecules. Now, it's very difficult to make a linear molecule and make it split into a ring. So our simple idea is you take a ring-like molecule, so something that looks like this, with a chain on the side, so something that looks like this. And the idea is the chain wants to be inside this ring, but it can't bend round to fit in this ring. So it finds another one. So this one fits into this daisy here, and you've got another one here. And this one, I've only got 2 hands, so I'm going to run out now, but this one goes into the next one, and the next one, and the next one. So you form this threaded polymer where you're not actually covalently bonding each of the monomer units together, but you're sort of threading one through the next, and so on and so forth until you get this chain. And it was a brilliant idea on paper, but it completely and utterly failed to work, which is fine in science. It often sends you down new paths. So what actually happens is your first one, you've got your ring and you've got your side chain, and your second one with your ring and your side chain. So what happens is this side chain goes into this ring, and then this side chain just simply bends back round and goes back through the first ring. And you just end up forming a dimer. It doesn't actually form a polymer. So it was a spectacular failure, but it was interesting science. So I never actually made any daisy chain polymers.
That's a nice explanation, Stuart.
Thank you.
My next question, what is self-assembly in supramolecular chemistry?
So self-assembly is just, supramolecular chemistry is basically non-covalent interactions. It's how molecules interact with each other through interactions that are not covalent. So you're talking about how molecules interact through hydrogen bonding, through metal ligand assembly, through pi-pi stacking, through van der Waals interactions, through the hydrophobic effect. It's how molecules interact with one another, but not covalently. And so that's the field of supramolecular chemistry. So supramolecular, it just means beyond the molecule. And that's what this is. It's about intermolecular interactions. And self-assembly is just how these forces result in assemblies of molecules. So you can self-assemble molecules into sheets or rings or chains if your project works. So that's what self-assembly is. So self-assembly relies very much upon supramolecular chemistry.
Stuart, my next question is, you and your colleagues have published a paper in 2002 named Covalent Chemistry. Now it has more than 1,000 citations. So I would like to know more about this paper, and can you briefly explain what covalent chemistry is and why is it significant for chemistry?
Sure. I feel like I'm in an interview for like a PhD position now, but this is a lot of fun. So that paper, it has so many citations because it's actually a review article. So it was a review article I wrote with Fraser and with another academic at Cambridge called Jeremy Sanders and a couple of other colleagues as well. And it's about, so covalent chemistry is when you form covalent bonds between atoms or different molecules, you stitch them together and you form a covalent bond. And most of the time you form a covalent bond, that's it. The covalent bond is formed and it's a kinetically trapped system. It doesn't go back. What we were doing with dynamic covalent chemistry, at least in the review article, we were surveying all of the examples of covalent bond forming reactions that are reversible. And there are quite a few of these. So for example, disulfide formation. If you take two thiols and you oxidize it, you can form a disulfide, but you can very easily reverse it to form two thiols by reducing it. Another example, which we use quite a lot, is imine formation. So an amine will react with an aldehyde to form an imine, but again, you can very easily reverse that. So it's about systems that are under thermodynamic control rather than kinetic control. And this is very important, especially in self-assembly, because it allows you to error check. So if you're building a big structure and you make mistakes, but all of your bonds are irreversible, you can't break them apart again easily. If you start making mistakes, you're going to get the wrong structure. But if you're building it using dynamic covalent chemistry, where the bonds can break and reform and break and reform, your system can sort of trend towards a thermodynamic minimum, and it will sort of error correct along the way. So we often use this to build interlock molecules and other bigger systems as well. So for example, if you have two separate rings, you can't thread one through the other. You actually have to open one ring before it will close in another. Now, if you've got a reversible covalent bond in this ring, this ring, if it's constantly opening and closing, and it's constantly doing that, if there's a thermodynamic driving force for it to actually form a complex with this ring and then keep opening and closing, it will actually ultimately trend towards this type of system rather than this sort of system. And then once you stop that reversible reaction, that dynamic covalent reaction going backwards and forwards, you can actually trap the thermodynamic product, which is this. So it's just a different approach to chemistry. So instead of making bonds that form and they're formed, you make bonds that can then be very easily broken and you can break the system apart again. It sounds a bit counterintuitive, but actually being able to make and break bonds is very important. We think about chemists making bonds all the time, but actually to make some bonds, it's also important to break bonds as well. So that's what dynamic covalent chemistry is all about.
Stuart, my next question is, could you please briefly explain us about bromine rings and what kind of specialty does it carry?
So I'm very much interested in interlocked molecules and different kinds of topologies you can have. So molecular borromine rings as an entity are entirely and utterly useless, but they are scientifically fascinating things. Now, the borromine rings themselves, let's forget about molecules now. The borromine rings are named after the Borromeo family of Renaissance Italy. And what borromine rings are, it's an assembly of 3 rings. And it's 3 rings that are all mutually connected to one another, but you can't break them apart. But they're only held together by virtue of the fact they're interlocked with each other. But it's actually really quite difficult to explain without pictures. But the really fascinating thing about borromine rings is no 2 of the rings are actually interlocked with each other. No 2 of the individual rings, but all 3 of them are held together because of the way they're arranged. And what that means is if you actually break any one of the 3 rings, it all falls apart. You're not left with 2 rings that are locked like that. Every single ring falls apart if you break one. And this was the emblem of the Borromeo family in Renaissance Italy. So you're talking the 1400s, 1500s. But this symbolism goes back thousands of years. It's actually used in Christian iconography. You can find it in illuminated manuscripts where you've got these 3 rings drawn in this way, because it represents the Holy Trinity. Because the idea is strength through the I guess I'm not religious, but the 3, what is it? The Father, the Son, and the Holy Ghost, or whatever it is in Christianity. And you've got strength through these 3 things all joined together. And if you break any one of them, it all falls apart. But it's seen in Norse mythology, it's seen in Buddhism, it's used as symbolism in a whole range of different things, not just Christian mythology, Christian iconography. But it's a really fascinating topology. So we wanted to try and build it out of molecules, because it's very easy to make a molecule where you stick 2 rings together. But how do you stick 3 rings together where no 2 of them actually do that and form this sort of interlock structure? And so it fascinated me, and I tried to come up with ways to make it. And eventually, as a team, we made it in Fraser's group. And it involves self-assembly pathways with 12 different organic ligands, 6 metals, and it all just comes together in one pot. And again, it's self-assembly, and it uses dynamic covalent chemistry, and it all assembles and it error corrects, and it just crystallizes nicely out of solution. And you get this beautiful looking molecule where you've got these 3 rings that are mutually interlocked with each other that won't fall apart unless you just break one of them, and then it will all fall apart. So it's completely and utterly useless. It will serve no application other than to maybe inspire people about how beautiful chemistry is, and just the sort of things you can make molecules do. The fact you can make molecules wrap themselves into these really intricate and complicated shapes. So yeah, that was my favorite project I worked on when I was a researcher in the lab.
That's great, Stuart. My next question, in your opinion, what was your most important scientific finding?
So that's really quite an easy question after the last one. I really think it was the self-assembly of the borromine rings, because again, it depends how you define important, and what's important to one person might not be important to another person. So the thing that was most important to me was that result, and just being able to make that molecule. And again, it doesn't have any application potential. It's not going to be used to save lives or make energy more efficient. It's just something that demonstrates the power of molecular self-assembly and the ability to build molecules. And so, as I say, even though it's not particularly useful in a practical sense, I think just to me, that was my most important result, because it just, it showed the power of what you can do with small molecules. You can make them sing and dance, basically.
Stuart, you are the chief editor of the Nature Chemistry Spring Nature. As the chief editor, why do you think that scientific publishing is important, and was there any special reason that paved the way for you to have a successful career in editorial realm?
So scientific publishing is important, but I think some people think it is important for different reasons than why it actually is important. And let me explain what I mean by that. Unfortunately, the way a lot of academics and researchers are evaluated today is based on how many papers they publish, where they publish their papers, the impact factors of the journals they publish in. And it's changed the incentives for how science is done. And people, I think, now tend not to do science because they want to find out about the world and they just want to advance our knowledge. They're sort of deliberately aiming to, it's not what scientific question shall I answer, it's, oh, what project do I need to work on to get my next Nature paper? And it's the wrong incentive. So, but unfortunately, that's the way academics are evaluated. And they're often evaluated, as I say, on all these publication metrics. And it is wrong. Academics should be evaluated on just the research they do and also the teaching they do and what they add to the community in general. But I think the true importance of scientific publishing is it captures a record of what we have done as a scientific community. And if we don't do that, we won't know what has been done and we won't know how to build on it. So that's what science is all about. Science is about building on what has been done before. No scientific project is ever brand new. It's always based on some principle or some other piece of work that has been done before. And if you don't capture what you have done and share it with wider society, how will they know that you've done it? So that's why I think publishing is important, not because of how it's used to judge people. That's not such a good use of publication metrics. Any reasons why I've had a successful career? Well, I guess it's subjective as to whether I've had a successful career or not. I enjoy what I do. I work with a really great team and we enjoy putting the journal out every month. It's a monthly journal. I'm passionate about talking about science and communicating science and making it easy for other people to share science. So I think that helps. I love writing about it. And I've just been lucky. I've worked with a lot of great people, and that helps. I mean, the journal is not just me. The journal is a massive team, and it's not just the editors. It's the people who work in our production teams. It's the people who get it up on the web. There are so many people behind putting out Nature Chemistry every month. So it's very much a team effort.
Stuart, this is my next question. As the chief editor, you have your own tasks and projects to take care of, and also you have overall responsibility for managing the journal. How do you manage all of these? Could you please tell us more about your experience at Nature Chemistry?
Yeah, it's a balance because so I still do a lot of what the other members of the team do. So I handle manuscripts. I read new manuscripts. I send them out to referees. I make decisions on manuscripts. I still edit things for the journal. So I commission people to write for the journal. I edit what they write. And that's essentially what all of the other editors do. We also travel and go to conferences when travel is a thing. And we go and give talks. And everyone does that. So in some ways, my job is the same as everyone else. But yes, I also have this additional responsibility of overseeing the journal, which means I need to make sure we have enough content, enough of the right types of content. Are we hitting targets in terms of the sort of content we need in the journal? How much content we need in the journal? How quickly things are getting into the journal? I also have to ensure that all of the appropriate policies are being adhered to in the manuscripts that we publish, and I help put procedures in place that make it easier for the editors to do their work. I come up with workflows. So it's you never really know. Each day is different. There's something will land in my email inbox every day that will be like, oh, okay, how do I deal with this? So you don't really need to know anymore a huge amount of chemistry. It's more about project management and time management and sort of you've got lots of moving parts, and it's making sure they all come together in sort of a harmony that makes sure it works when we actually put out a journal every month. So it's certainly challenging, but I've been doing it for quite some time now, so I'm quite familiar with the sort of challenges it throws up. So yeah, it's lots of different things and making sure everything runs smoothly, and it takes a lot of time.
Stuart, Nature Chemistry is a scientific journal that offers a unique mix of news and reviews alongside top quality research papers. In your point of view, what is the main contribution of this journal in the field of chemistry?
So, I mean, we're just a journal, and there are lots of very good journals, and people can decide whether it's a good journal or not. It's up to the community to decide whether Nature Chemistry is a good thing or a bad thing. It's not for me to say, because I'm obviously quite biased. So I like to think that we publish interesting papers that I hope our audience will find interesting and hopefully sometimes useful. And on top of that, we layer sort of non-research content. We get people to write analysis of recent papers. We also get people to write review articles on particular topics. We also have very interesting articles about just other things in general, such as diversity issues, such as we have an essay coming up about lithium-ion batteries, and everyone wants an electric car, but we're going to run out of lithium in 40 years time. So what are we going to do then? So we need new battery technologies, things like that, and how chemistry impacts everyday lives. So the main contribution of Nature Chemistry, we're a journal that filters a lot. We reject a lot of submissions because not because they're wrong, not because they're bad, but just because we're slicing off what we think is the very best in chemistry, and we're presenting that to our audience. So we're acting as a filter. I mean, a lot of the work that gets submitted to us that we decline will be published somewhere. It's just we're sort of like we're like the chemistry highlights, if you will. We're publishing what we think are the very best research papers, but it's just our opinion. And we're publishing what we hope is additional interesting analysis from people in the field who have something to say. So that's what I think the impact of Nature Chemistry is, but really it's not for me to say, it's for the readers to say, because they're the ones who can critically evaluate what our contribution is.
Stuart, would you please give us a brief history of the journal?
Absolutely. So, so I actually started as an editor with Nature Publishing Group back in 2006. Excuse me. And I started on a journal called Nature Nanotechnology, which launched in 2006. And even then, so there wasn't a Nature Chemistry then. Nature Chemistry did not exist. But there was talk in the company about how, we should have a chemistry journal, because they had Nature Physics, they had Nature Materials, they even had Nature Chemical Biology. And of course, they were just launching Nature Nanotechnology. And so a bunch of chemists in the company got together with some of the decision makers, and we actually had like a 2 or 3 day strategy meeting in Boston in the US, talking about, should we launch a chemistry journal? And we looked at the sort of chemistry submissions that were coming into the company as a whole, and how good were they, and could we sustain a chemistry journal? And to be honest with you, it was a fairly easy decision. So in 2007, we started recruiting, and I applied to be the chief editor. And I was fortunately successful in that. So I became the chief editor on February the 1st, 2008. So then I had to recruit a team and essentially put everything in place for the journal. There's nothing there. There's literally no website, nothing. So you have to do everything from scratch, which is kind of exciting and challenging. And then our first issue was the April 2009 issue. So we had just over a year lead up time to the first issue. And it's great. You've got all this time before the first issue, so you can make all these great plans. But then suddenly a month after the first issue, you have to put out the second issue. Then a month after that, you have the third issue. And a month after that, the fourth issue. And it never stops. So you never have as much time as you have before the first issue. And it's just carried on from there. I mean, we've had a little bit of turnover on the editorial team. A few people have left and gone to different journals or have gone to work on, and it's just sort of grown. Our submissions have grown, the number of papers we publish has grown, the types of content we publish has become more varied. So yeah, it's we're now in volume 13, I think, or something like that. Yeah, so that's it. I mean, it's a fairly, still, relatively speaking, it's quite a young journal. I mean, JACS has been around for, what is it, 150 years or something now, and Angewandte in one form or another has been around for decades. So we are still a very, very young journal. So what are we? If we're 12 years old, we're coming into our difficult teenage years as a journal. So maybe we'll start behaving badly soon. I don't know.
Stuart, my next question is also about the journal. Recent analysis shows that the journal Nature Chemistry is having a growing impact among journals in the field of science. What do you think about this achievement of Nature Chemistry?
Well, again, it's mostly a reflection of this filtering, in that we really are selecting what we think are the very best papers. We're skimming off, hopefully, what we think are the really interesting things. So the papers in Nature Chemistry do tend to get a lot of attention. That doesn't mean everyone thinks every paper published in Nature Chemistry is a great paper. Some people will think they're great papers, some people won't. I don't know. We're just having a good time finding what we think are interesting papers and then putting them into the journal. People should not put too much importance on any given journal, because it's not really the journal that's important, it's the work that is in the journal. And just because it's in a particular journal doesn't make the work any better or any worse than if it was in any other journal. It's the work itself that is the thing that you should be applauding, and it's the research that is really influencing the chemistry community. Having said that, I mean, if you write editorials that resonate with people and you attract content that people really enjoy and people think will maybe have an impact on chemistry, that's great. But again, it's not for me to say what our impact is. I'll leave other people to judge that. As far as I'm concerned, we're just a chemistry journal, and if people think we're a good journal, great. And if people don't think we're a good journal, I'd like them to tell me why, and we'll try and fix it.
Stuart, what are the skills that we need in career in the publishing business, such as editorial work?
So I can only really speak from what I look for in candidates when I interview people to be editors. Different people might look for different things. As far as I'm concerned, the most important thing is I just want people to be passionate about science and passionate about communicating science. Because if you find reading papers boring, you're not cut out to be an editor, because that's mostly your job, is reading papers and assessing papers. So as an editor, you need to be able to assimilate information quite quickly. And sometimes it can be quite complex information. So you need to be able to digest that information and then make a decision about whether that's the sort of thing that would be good for publication in Nature Chemistry, or maybe not so much. You also need to be good with people, because obviously you do spend a lot of your time telling people that, I'm really sorry, this paper isn't quite there for us. It's not what we're looking for in the journal. And as a Nature journal, where we reject 90% of everything that's submitted to us, you do spend a lot of your time giving people bad news. So you have to be you need to be able to interact with people. You need to be able to go to conferences and be able to talk to people and find out what they find exciting, and maybe sort of encourage them to send their next great paper to your journal. So you need to be very much a people person. You need to have a broad awareness of what's going on in chemistry. So researchers tend to drill down ever deeper into an ever narrower area of chemistry. That's what researchers do. As an editor, we need a broad perspective across all of the things that are going on in chemistry, the emerging topics that are going to be important next year or the year after, and sort of try and move with the times. So there's that. You also need to be very good at time management, because the publishing business is very much about deadlines. You can't publish your April issue in August. People would get quite cross. So you need to manage your time very well. And it's quite unstructured work, because it's not like you start every day with a set series of tasks that you have to complete by the end of that day. in some ways, it's almost like being an academic. You have to be very self-motivated. You have to decide which task gets the higher priority today and which you're going to do first. And so there's a lot of balancing there. But to work in publishing, you don't need to have any prior publishing experience. You don't need to have published a huge number of papers. I don't recruit people because they've published 25 papers. I recruit people because they can assess what other people have published and they can make decisions that they can explain and justify, and which they can do it quite efficiently and quite quickly as well. So it's really just about having a broad awareness of the field and just being good at time management and just being excited about science. Because if you can't get excited about the papers you're reading, then you're never going to want to publish anything.
Stuart, you are currently blogging at the Chemical Connections about the chemistry and related topics. So we would like to know about the different aspects of chemistry in the modern world.
So the way people communicate has obviously changed quite a lot over the past 10, 15 years. I mean, the internet has changed everything. We wouldn't have been doing this 15 years ago. So obviously there are now blogs. I actually haven't blogged at that blog for quite a while because I've been quite busy, but I should do more. But there's obviously now lots of different forms of social media. So people use Twitter as a communication medium, also Facebook, also Instagram as well. I mean, there's so many. I'm so old now, there are social media networks I've never even heard of that exist and I've never used. Like TikTok, people are using TikTok to explain chemistry. So there are many varied and different ways to communicate chemistry in the modern world, which is a good thing because it's great that we're not just all sitting around reading big textbooks anymore. And the variety of ways you can receive the information probably means that you will suck in more of that information. The challenge with chemistry in particular is it's sometimes quite difficult to explain to a broad audience what the importance of chemistry is, because a lot of people think of chemistry as sort of petrol or washing powders, or because they don't necessarily equate chemistry with sort of life-saving cancer drugs, because that's medicine. But the fact is to actually get to the point you're making a life-saving cancer drug, you need to go all the way back to the start of the pipeline, and that was biology and chemistry. So some biologist figured out that, oh, there's a protein here, you can target that protein, you need a molecule that looks a bit like this to target it. Then along comes a chemist and goes, right, I know how we can make that, and they develop ways you can make it and make it efficiently and make it on large scale. And so, but all the public sees at the end of the day is, wow, look, we've got this new medicine, and it's not a chemical, it's medicine. So there are challenges trying to get across the importance of chemistry. And I think it's because chemistry is so interwoven across the entire fabric of science that it's difficult to pick out the specific thing that chemistry does. Because if you talk about physics, you've got planets and stars and spaceships, and you've got a large hadron collider, and you're smashing particles together. Boy, that sounds exciting. Biology, you've got genes, you've got the human genome, you've got life, you've got genetics. Wow, that's fascinating. Chemistry, what you got? SN2 reactions? That's hardly going to get people talking, is it? So it's a little bit difficult. There are challenges in particular with chemistry that make it a hard subject to sell in terms of the popular press and that sort of thing. But there are ways of overcoming that, I think. And there are science communicators who do a really good job of that, but they're much better than me at doing that. So yeah, those are the challenges, I think. And I need to blog more. That's the answer to your question.
Stuart, you have been fortunate to receive several awards such as Winston Dissertation Award in 2000, Cram Research Award in 1999, and Franklin Prize for Excellence in Practical Chemistry in 1995, etc. What led you to achieve those awards, and how those helped in your outstanding research investigations?
So the dissertation award, I guess, was for the work I did during my PhD, as was the Cram Research Award. So I guess people liked what I did for my PhD, and perhaps I communicated it quite well. The Practical Chemistry Prize was something as when I was an undergrad. And I think I just did well in labs, which surprises me today because I probably shouldn't go anywhere near a lab. But apparently when I was an undergrad, I was quite good at it. So awards mean very little, to be honest. I mean, they're in the moment. It's great to get the recognition. But I mean, I maybe won one of those awards just by beating someone else by 1 point. And if I'd got 1 point fewer, maybe someone else would have won it. So you shouldn't measure yourself by the awards other people give you. You should measure yourself by the things that you do, the things that you learn, and the things that they mean to you. So did those awards help me? Probably not. It was great to get them, and I'm very thankful that I did get them, but I don't think it's necessarily changed my career path or changed how I've gone about things. Again, it's almost like, researchers shouldn't do their research by targeting what do I need to do to get this paper in this journal. Similarly, you should never just do your work to try and target awards. What do I need to do to get this award? That's the wrong sort of motivation to try and do something. You should do things in life because you love doing them and you just enjoy those things. And if you get rewarded for them, great, but your reward should just be that you're enjoying what you're doing.
Stuart, overcoming challenges is a really important
from them and finding better ways to do things. Because actually, if you never failed at anything, you probably wouldn't necessarily improve beyond where you currently are. Because if it seems like if you're doing everything right all the time, you're never going to stop and question yourself about, is this the right approach? Am I doing this correctly? So it's important not to get disheartened. It's important to talk to other people, who've gone through some of the same challenges, so you can see that there is sort of light at the end of the tunnel, and other people, so you're not alone. That's another important lesson here, is you're not alone in facing these challenges. Other people are probably going through similar challenges now, or have gone through similar challenges in the past and have come through them and have learned from them. So so how do I personally deal with challenges? I reach out to trusted colleagues and I like to talk through things with people, see what they would do, see what advice they have to give. It's important to remember you're not alone. So there's a community around you no matter what you do, and it's useful to tap into other people's expertise and experiences too.
Stuart, now we have more general questions for you. According to your opinion, what are the traits that are critical to become a scientist?
That's a deep question. I think you need an innate curiosity. You need to constantly question things. You need not to accept things at face value. You need to have a desire to understand the inner workings of the world and not just take things as they come. So it's always the children as well who constantly ask questions about, well, why does it do that? Why is the sky blue? Why does the sun rise from that direction in the morning? Why does it set over there? So you need just to be curious about things. You need to want to find answers to questions. You do need to be hardworking. That's not to say that you have to work 7 days a week and crazy hours every day. But when you are working and being a scientist, in fact, being a scientist is more of a state of mind than it is a job, actually, come to think about it, because you kind of live your life like that as well, sort of constantly questioning, well, why does that happen? Why does this happen? And I think we do tend to lose that a little bit as we get older, because we don't have that sort of childlike curiosity, and some of the magic of how things work gets explained to you, and it's no longer this sort of big, wow, that's how it works. So you kind of have to try and retain that sort of curiosity. What else is critical? I think the idea of being a lone genius, that was maybe something that was important 100 years ago, when it used to be old white men working in their large basement, doing reactions with things they got from the local hospital or whatever. But science today is more about teams. It's about working as teams and collaborating with other people, being open to new ideas. That's there you go. There's another thing you have to be good as a scientist. You have to be open to new ideas, and you have to be able to accept you might have got things wrong, and you have to be able to change the way you think about things. if you get sucked into a particular dogma and then you will not accept that that might be wrong and other people can't change your minds, then that's game over. You have to be able to go, okay, I thought it worked this way, but you've now shown me the evidence and I agree with you, it doesn't work the way I thought it does, it now works this way. So you have to be open to that. And so you have to be, again, you have to not be afraid of failure, not be afraid of getting things wrong, learn from your mistakes and move on from things that have just proved not to be right. So there you go. That's a few minutes of waffle about hopefully what it takes to make a good scientist.
Yeah, Stuart, I also think that those traits are extremely important to become a scientist. And my next question is, should scientists do work that has a direct impact on society? What is your opinion?
Yeah, it's a very good question. There are two sides to this, because a lot of science is funded by the taxpayer. And so you can say that the science then should have a direct relevance on society because it's being paid for by society. The problem with that approach is sometimes you work on a piece of science and you don't know what the relevance to society is. It may have an amazing amount of relevance, but at the time you're doing it, you just might not know. It might take 5 years for that piece of work to become relevant and impactful. It might take 50 years. I mean, the first paper on graphene, on making graphene, was I think in the 1950s. And we can still argue about whether graphene has actually done all that much for society, but obviously it won a Nobel Prize in physics maybe 10 years ago now or longer. And so obviously it's had a huge scientific impact, but it took a long time for people to realize that, oh, hang on a minute, this material we might be able to make it and it might be used for something. So, and it's the same with things like protein synthesis and DNA sequencing. I mean, when DNA sequencing was first developed, did it have a massive impact on society? Probably not at the time, because we didn't have the tools in place to be actually able to apply it. But now it's obviously crucial to so many things in medicine and forensics. So that's the problem, is you could say, okay, we will only fund projects that have a direct social relevance. But how do you judge that? How do you know? And you might be denying funding to projects that might turn out, if they had gone ahead, that they might in 20 years lead to a new breakthrough in solar cells that means that we never have to burn fossil fuels again. You don't know. The reason it's called research is because it is research. We don't know the answer. So it's a difficult one. I don't think people should be taking taxpayers' money and just wasting it by doing things that are utterly never going to be important to anyone. But again, how do you make that call? How do you decide? I mean, it might be that there's one scientist who looks like a mad scientist who it seems like their projects are completely useless, but turns out to be a genius. I mean, the people who are 20 years ahead of the time, crazy scientists, because people are like, well, why are they doing it? They might turn out to be prophetic. So it's hard. I think ultimately, yes, science should have an impact on society, but sometimes it takes so long to figure out what that impact is that we should still be able to fund some blue sky research because we just don't know if it will be useful or not.
That's a great explanation, Stuart. So in your opinion, what will be the next great breakthrough in the field of science?
Whoa, again, you're asking all the big questions. Well, the honest answer is I have no idea, but I can probably make some guesses. So I think the one area where I see a lot of research where I think there could be a massive breakthrough is in battery research. I mean, batteries are clearly crucial to so much of the modern world, and I'm talking like batteries for portable devices. And so, I mean, imagine your mobile phone, your cell phone. I mean, I have to charge mine every night because the battery only lasts a day. That's probably because I'm using Twitter too much, but it only lasts a day. Imagine a breakthrough in battery technology that means you only have to charge your smartphone once a week. Maybe you can make batteries that are even smaller than they are now. And this goes back to the electric cars argument as well. So I don't know if there's going to be, but there could be a massive breakthrough in battery technology related to energy, also solar energy and solar cells. There's obviously a lot of research done. Initially, it was on dye-sensitized solar cells. Now people are looking at perovskites for solar cells. And again, if we can have a really good, cheap material that is very efficient at converting sunlight into energy, that would be amazing, and it would reduce our reliance on fossil fuels. So that could be a breakthrough. But also, I mean, things that are also happening now. So CRISPR, obviously the DNA editing tool, just won the Nobel Prize last year. I guess the first steps are now being taken in terms of DNA editing for medicine. And that has a bunch of ethical questions as well. But the fact we now have so much control over our genetic makeup, there could well be huge breakthroughs there as well, in terms of maybe we'll be able to eradicate some genetic diseases that we otherwise wouldn't by being able to edit our DNA. So, but that's the great thing about research. I don't know. It'll be a surprise, hopefully, and it will take us all by surprise, and we'll all go, wow, that's fantastic. But those are some areas where there might be some breakthroughs.
Great, Stuart. I think we have come to the end of the session. So my final question is, what kind of advice would you have for someone who may be interested in working in this field?
So do you mean the areas I've just talked about, or do you mean working in scientific publishing?
In both, like scientific publishing and research area.
Okay. Just follow your passion. Do what it is that gets you out of bed in the morning. If you want to work in scientific publishing, then get more familiar with the publishing process. Learn how scientific journals work, what it takes to be an editor. If you want to work in a particular field of research, look at the people who are already working in that area. Look at what it takes to get to that point, what sort of courses you might need to take to be able to work as a PhD student in that field. It's about awareness of what's required, and it's about connections. It's about getting to know people who work in those fields, so you have someone who you can ask questions of, who you can ask for advice from. But there's no one size fits all recipe. There's no blueprint for, I want to work in this area, this is how I'm going to get there. That's the great thing about science, is people can switch what they do in science fairly easily. Actually, it's easier earlier in your career, I think, a little bit, but there's no one pathway, there's no one route. We all take different paths. I mean, 20 years ago, I didn't know I was going to be the editor of Nature Chemistry. 30 years ago, I probably didn't necessarily know I was going to be a chemist. And I kind of just chanced into that. I didn't grow up wanting to be a chemist. And I tried physics first, as I said at the start. I tried a physics degree, and that was a total failure. But I moved on and I chose chemistry instead. So again, don't get disheartened by thinking, oh, well, there's no path for me, because maybe you'll take a different path. Maybe you'll take a path that no one has taken before. Maybe you'll blaze a trail to go and work in one particular field. So there's no real single answer to that, I would say.
And the advice you gave are really useful for us as budding scientists. With that, the time has come to wind up the interview. We had a fascinating interview with you, Dr. Stuart. Thank you very much for joining with us and sharing your knowledge. It was a great privilege and honor for us to interview you.
For me too, thank you. It was really interesting talking to you all.
Thank you once again on behalf of the Department of Chemistry, University of Colombo. This concludes today's interview with Dr. Stuart Cantrill, the Chief Editor of Nature Chemistry. We really appreciate that he was able to allocate his precious time to take part in this interview. Dr. Stuart, good luck in all that comes your way in the future. I hope it goes well for you.
You too.
We believe that this interview will inspire and encourage our scientists who are willing to make their mark in the field of science. And thank you everyone for joining with us today. Stay tuned with us to have more interviews with eminent scientists all around the world. Have a nice day.